AP Physics, we're on to our last unit and our last lesson. It's on Unit 6, which deals with simple harmonic motion. So simple harmonic motion, which is abbreviated SHM, is a repetitive oscillation around an equilibrium. Two variables are used in simple harmonic motion. The frequency, which is the number of cycles per second, and the units for that are hertz or 1/s. Frequency is given by the equation frequency equals cycles per second. So a cycle is one entire movement through the wave. So you go from the top to the bottom and back to the top again. That would be one cycle. How many times you do that a second is the frequency. Units for frequency are hertz or 1/seconds or seconds to the negative first. Those all mean the same thing. The period, which is abbreviated by a capital T, is the time required to complete one cycle. So the period is given by the equation 1/frequency. So they're both reciprocals of each other. And the unit for period is some unit of time, usually seconds. Alright, so let's do a problem here. What is the force constant for the suspension system of a car that settles 1.2 centimeters when an 80-kilogram person gets in? Okay, so lay out what the variables are that you're looking for and that you have. You're looking for a spring constant here. What you have to work with is the displacement, 1.2 centimeters, the mass, 80-kilogram person, and since we're talking about an up and down motion type of problem, you're also going to need gravitational acceleration. Okay, so we're going to choose a formula. It's the spring constant formula that we've used before. Force equals negative K times X. We've seen this formula earlier in the course. So we're going to solve that for K. We have K equals negative F/X. So we plug in the numbers. First, we're going to convert from centimeters to meters. Everything has to be in meters when you deal with these types of problems. And there you have it. You plug in the kilograms times the gravitational acceleration will give you the force, that's the weight. And you have the X, the change of position, and that gives you a spring constant, or force constant they call it here, of 6.53 times 10 to the 4th Newton meters. Alright, we can use a toy gun's spring mechanism to ask and answer two simple questions. How much energy is stored in the spring of a toy gun that has a force of 50 Newton meters and is compressed 0.15 meters? So we're trying to find the potential energy. That's the potential energy because a spring only has potential energy. Okay, what's in the toolbox? We know the spring constant. We know the displacement, and so the potential energy for a spring is given by 1/2 spring constant times displacement squared. So this is a pretty easy problem. You plug in the numbers and calculate, and you get it 0.563 Newton meters, which is also another way of saying a joule. A joule is a Newton meter. Okay, same data set. It says if you neglect the friction and the mass of the spring, at what speed will a 2-gram projectile be ejected from the gun? Okay, so that we're looking for a velocity, and we have the mass of the projectile is 2 grams, and you need to convert that to kilograms. We need to always convert centimeters to meters and grams to kilograms in physics. Okay, so we have the potential energy in the spring is all going to be converted into the kinetic energy of the projectile. And we have that, we have the potential energy of the spring from the last part of the problem, part A. So we know that's going to equal both 1/2 kx squared and 1/2 mv squared. So what we're trying to find is the velocity. So now we just have to do some algebra. We multiplied both sides by 2. And we see the 2's cancel there, or by 2m actually, and we have the masses cancel there. Okay, so we have V squared equals 2K equal over M. To get V, you take the square root of both sides. We're going to plug that in, and we come up with an answer of 23.7 meters per second. Now the unit for the answer will be joules per kilogram, the square root of joules per kilogram. That's the same as meters per second. Don't worry about the units in this case. Okay, a medical imaging device produces ultrasound by oscillating with a period of 0.4 microseconds. What is the frequency of the oscillation? So again, your sheet and the official AP sheet also will tell you that that symbol is microseconds. That's 10 to the minus 6th seconds. So what are you solving for? Frequency. F equals question mark. Okay, what is in the toolbox? The period. It's 0.4 microseconds. It's given to you. So you're going to convert that into scientific notation in seconds. So 10 to the minus 6th, you move the decimal over one position, and you get 4 times 10 to the negative 7. Microseconds cancels, and there you go. Okay. So frequency is 1 over the period. Plug in the numbers. Pretty simple process here. And you get a frequency of 2.5 times 10 to the 6th. You can call it 1 over seconds or hertz. So that's 2.5 million cycles per second, hertz. Okay, the frequency of middle C on a typical musical instrument is 264 hertz. What is the time for one complete oscillation? It's another way of saying a cycle. It's up, it's start at the top, go down, come back to the top again. That's one cycle or oscillation. So we're looking for the period. How long does it take for one cycle or one oscillation to occur? Okay, so there we have the frequency, 264, and I prefer that you use 1 over seconds because it's better if you need to cancel with seconds somewhere along the way in the equation. You can do it. Hertz doesn't cancel with anything, but 1 over seconds can cancel. The seconds can cancel. Okay, so the period equals 1 over the frequency. Plug in the numbers, and you get an answer of 3.79 milliseconds. Simple harmonic motion, abbreviated SHM, is a repetitive oscillation around an equilibrium. The two types of simple harmonic motion covered on the AP Physics test are a spring and a pendulum. A spring can both extend and compress. A spring that can both extend and compress can exhibit simple harmonic motion. The equilibrium position is where the spring will rest. So if you just let it go, wherever it settles, that's the equilibrium. The amplitude is the maximum distance from the equilibrium the spring either stretches or compresses. A cycle is a complete movement from the top to the bottom and back to the top again. So what you see is that spring on the left is compressed up to the top. It then goes down to the bottom. It comes back up to the top. That's one cycle. In the previous problem, we heard that was called an oscillation also. Okay, so spring can both extend, and compress, can exhibit simple harmonic motion. The frequency of a spring mass system is, frequency is 1 over 2 pi times the square root of the mass divided by the spring constant. So the only two things that affect how fast that spring is going to go up and down are the spring constant and the mass that's hung on the spring. The period of a spring mass is going to be the reciprocal. So it's going to be 2 pi times the square root of k over m. Key point, the frequency and period of a spring are a function of the mass hanging from the spring and the spring constant. Okay, so if the shock absorbers in a car go bad, then the car will oscillate at the least provocation. That means something causing it to bump up and down, such as when going over bumps in a road. Calculate the frequency and period of these oscillations for such a car if the car's mass, including its load, people sitting in it, is 900 kilograms and the force constant K of the suspension system is 6.53 times 10 to the 4th Newton per meter. So we're looking for the period and the frequency. What's in the toolbox? You're given a mass of 900 kilograms. You're given a spring constant. There, you see it there. So we're simply going to plug those into the formula, and then we're going to take the reciprocal of that to get the period. So there's the formula for the frequency, and it gives you 1.36 hertz or 1 over seconds. The period is going to be the reciprocal of that. It's going to be 0.74 seconds. Okay, the other type of simple harmonic motion involves a pendulum. A pendulum is a mass attached to a rod or string with a pivot above, such as attached to the ceiling. The equilibrium position is where the pendulum will rest. The amplitude is the maximum distance or angle the bob swings from the equilibrium. The bob is whatever the weight is at the bottom of the rope or the string. A cycle is a complete movement from one side to the other and back. The length is the distance from the pivot to the bob, so it's the length of your string. Alright, the formulas for a pendulum are: for the force on the bob of the pendulum, force is approximately equal, but close enough that you can use this, is negative the mass times gravitational acceleration times the angle you're pulling the bob back to one side. The period T is the time required to complete one cycle, and the equation for the period is, it's 2 pi times the length of the rope or over the gravitational acceleration. So the key point here is the period of a pendulum is a function of the length of the rod or the string. The mass and the amplitude do not affect the period. So what is the acceleration due to gravity in a region where a simple pendulum having a length of 75 centimeters has a period of that number right there, 1.7357 seconds? So what are we solving for? Gravitational acceleration. It's the only acceleration that the pendulum is experiencing. So we're using basically this experiment to determine the gravitational acceleration. So what's in the toolbox? So you have a period given there. You have the length in centimeters, which you convert to meters, 0.75 meters. So the formula, we're going to take that formula right there, and we're going to solve it for G, because that's what the question's asking for. So we're going to square both sides. That means we're going to get 4 pi squared over LG without the square root sign. And that, if we solve for G, then multiply both sides by G and divide by T squared, we get G equals 4 pi squared length over period squared. Now we have all those numbers, we can just plug them in, and we get G equals 9.8281 meters per second squared, which is pretty close to what we know it is. Okay, that takes care of this very brief lesson and unit on Unit 6. And we're going to deal with more questions as we go through the spring. So this is not all there is to it, and you'll have your share of AP type questions to do.